ECP bi-weekly seminar series. And we are excited to have Mr. Edward Garza with us today. So Mr. Garza is the Assistant Manager of the Office of Environment, Safety, Health and Quality Assurance for the Waste Isolation Pilot Plant, which is the WIPP, for the Carlsbad Field Office. He's responsible for the safety of all operations at the WIPP site. Mr. Garza has a Bachelor of Science degree in chemistry from Texas Tech University, and he has around 34 years of nuclear industry experience within the DOE complex. Mr. Garza worked at the Advanced Test Reactor at the Idaho National Lab in operations from 1988 till 2006. He was a shift supervisor of one of the ATR operating crews and also held the positions of outage coordinator, emergency action manager, lead nuclear simulator instructor, and nuclear training supervisor for operations and technical staff. Mr. Garza joined the Department of Energy in November of 2006 as a facility representative and performed oversight at all EM facilities at the Idaho National Lab. He was twice selected as the Idaho DOE EM Facility Representative of the Year. In 2014, he became the Senior Facility Representative at the Advanced Test Reactor. While at ATR, he was deployed on 2 occasions to WIPP to assist with the initial stages of recovery following their fire and contamination events of 2014. Mr. Garza joined the CBFO team in Jan of 2015 as the Facility Oversight Division Director building a new FR program and oversight processes for the CBFO. In August of 2016, Mr. Garza took over as the Assistant Manager, and he successfully guided the CBFO through the DOE Operational Readiness Review for the restart of waste emplacement and the restart of waste shipping to WIPP. Mr. Garza's expertise is in nuclear operations and oversight. Since 2006, he has provided oversight and directed offices in the coordination of oversight at multiple DOE sites, including the INL, the Separations Processing Recovery Unit site in Nishkauna, New York, and WIPP. His expertise includes all areas of conduct of operations, industrial hygiene, radiological controls, fire protection, nuclear safety, technical safety requirements, configuration management, ISMS, industrial safety, OSHA, Code of Federal Regulations, Life Safety Code, hoisting and rigging, RCRA, CERCLA, TSCA, quality assurance, environmental compliance, critical safety, contractor assurance and training, and MSHA. Mr. Garza goes by Ed to all those who know him. He is a former trainer of Arabian show horses, an avid golfer, a once upon a time expert skier, a recent amateur brick mason, and always a rabid Texas Tech football fan. So, with that, Mr. Garza, the floor is all yours.
Well, thank you very much for that introduction. And had I known you were going to read it, I wouldn't have made it so long. So I apologize for that. First of all, let me say that it's a privilege to be able to present to this organization. I have a very deep respect for the CRESP organization and for the team. CRESP was very helpful to the Carlsbad Field Office and to our facility when we were recently starting one of our old legacy waste fans, which provides ventilation into our underground. So I have had the privilege of working with Dr. Cosson and some of the other esteemed professors in the organization. So this is a privilege for me. Thank you very much. Today, I wanted to talk to you about what is, in many cases, kind of an unknown about the WIP facility. And one of the things that makes us very, very unique in that we have an operating mine that we have to manage. And in that operating mine, we're also housing a nuclear facility. And I will tell you very shortly about what WIP is and what we do, but I want to emphasize today that the uniqueness of this challenge that we have, because we're conducting this nuclear operation inside of a bedded salt mine, 2,150 feet underground in the earth. And that makes us a very unique facility and comes with its very own challenges, and I want to make sure that everybody appreciates what those challenges are. So the picture you see behind me is actually one of our continuous mining machines in our underground. I was just telling Jody that we painted orange because we wanted to look pretty, but it's a very useful machine. It has an interesting utility in that it's able to mine all of this salt that we have in our underground, collect it for us in a central conveyor belt, and then put it onto trucks that we can then haul it out of our underground. But it's operated remotely. So there is not an operator on the cab of this vehicle. There's actually, as you see in the picture above me, an operator with it's a little box that's on his waist that he controls it from, all automatically. And so no one is actually driving this vehicle. A very large Radio Shack controlled vehicle is what it is then, just sort of as a metaphor. So going to what WHIP is, first of all, you need to know where we are located. So I think you can see here on the slide that WHIP is located in the southeastern portion of New Mexico. We're 30 miles east of the city of Carlsbad. You see the star on the map there, very, very low corner, southeastern corner of New Mexico. And we're in what we call the Chihuahuan Desert. There's a picture that you see there next to the picture of the state. That's actually a truck and tractor that is bringing one of our shipments into the WHIP facility. You can see 3 casks that are on that trailer. That's what the waste is packaged in and transported over United States highways from all over the country. And then in the background, you can actually see the skyline, if you will, of the WHIP facility. So we'll go on to the next slide. Okay. So what is WHIP? Is the question we get quite often. We are the nation's deep geological repository for defense-related transuranic waste. The facility is owned by the Department of Energy, and it is operated by a contractor that we contract to run the facility for us. We currently have started a new contract with a company called the Salado Isolation Mining Corporation, which is abbreviated into SIMCO. You might even hear me say the word SIMCO on occasion here as we're talking. Again, it's owned by the DOE, but operated by a contractor for the DOE. Transuranic waste, defense-related transuranic waste, is the byproduct of the production of our nuclear weapons cache in the United States. Many people don't know, but over the years, since 1945 in the Manhattan Project, the United States has built in the neighborhood of 32,000 nuclear warheads. And the complex, in order to do that operation, is very large. It's dispersed throughout the United States. And in the process of doing that, as you make nuclear weapons, everything that is in the production process at some point has the opportunity to be what we call contaminated with this thing that you may have heard of, plutonium and uranium. Plutonium and uranium, of course, are radioactive components, they're radioactive isotopes. And for that reason, if you make waste that has some element of that in it, plutonium or uranium, or any of its decay byproducts, you just can't put that into a regular landfill. So it has to go to a special repository that wouldn't have the possibility of contaminating the environment, and that's what WHIP is. We are that repository. We're located 2,150 feet underground in a salt formation that's known as the Salado Formation. And the Salado Formation is a thick, ancient deposit of layered halite, rock salt, which is over 1,500 feet thick in this area of the country. The remains of an ancient ocean, the Permian Sea, as a matter of fact, which evaporated over 250 million years ago. That's at least what the scientists tell me. So it's really an astounding geological formation. Starts in southeastern New Mexico, and it goes all the way up through West Texas into Kansas, as a matter of fact. So the remains of a very ancient ocean that over time evaporated, leaving this large salt deposit behind. The mine, WHIP, is actually just about in the middle of that formation. here in southeast New Mexico, and it is mined at a single horizon. So there's only one level to our mine, as you can see in that graphic. There are not multiple levels like you might see in a movie about a mine or mines. This is all at one level, 2,150 feet deep. We can access the mine or the underground via four shafts that come from the surface. So when we receive the waste, we receive it on the surface at our surface facilities, and we will remove the waste from those casks that I showed you in that first picture, and then we will put them onto a conveyance and then take them into our underground, where then they will be trucked on flatbed trucks that are of specific design, and then taken to a specialized room that we have prepared in advance for that waste to be taken down into the underground. Now, in our history, we've been operating since 1999. The WIP site is approaching its 14,000th shipment from different sites across the country. And we have a transport contractor that does that specifically for us. It's called CAST, pardon me. And they are approaching their 16 millionth safe mile of operation, transporting that waste over United States highways to our facility. So something we're very proud of that we're doing. And once we get it here, we take it in the underground. It goes into the different rooms, and then we just do it over and over again. So the thing about that is that in order to do this operation, we have to operate the mine. So I will go to our next slide here. So one of the questions I often get about WIP is, why would we do this operation in a salt mine? Why halite or rock salt? Rock salt is known as halite in the mining community, and it has many favorable characteristics for this type of activity. So salt is essentially a plastic medium. So what that means is when you drill into salt, let's say that I drill a hole into rock salt, the forces that are felt by that rock salt will actually cause the salt to flow into that hole. So if we put transuranic waste into a room that we've mined into rock salt, that salt will over time slowly fill in that void space and encapsulate that waste for perpetuity, which is the reason that we're doing an operation like this in a salt mine. It was actually a study that was done by the National Academy of Sciences back in the early 50s to decide what we would do with this issue of transuranic waste. So you see a picture there, a graphic of the rock salt, not a graphic, an actual picture of rock salt that you see right there. It's interesting. Rock salt weighs about 135 pounds per cubic foot. So, you know, a cubic foot is about this dimension, and that's going to weigh 135 pounds. And so you can imagine that there are tons and tons of this that we have to deal with when we're doing this operation. In a salt formation underground, the weight of the earth above the mined opening is going to apply pressure on all of those openings as the salt is flowing in or trying to move in. That's actually what causes that pressure. It's the weight of the earth above it. We call it lithostatic pressure. And so it's pushing the salt into that opening, trying to encapsulate or close up that opening. And that's continuous at all times. It never stops. And the trick for us is that we have to be able to allow that to occur in the rooms in which we place the waste, but the rooms that we use to get to, or the drifts or access tunnels that we use to get to those rooms, we have to keep those open without encapsulating us while we do that activity. So that is really our challenge. The WIP facility has some openings, tunnels, which, by the way, we call a drift. They have been kept open now for over 30 years, which is really a challenge in the mining world. So every opening in the mine, as I said, is continually experiencing the forces from this lithostatic pressure. And the forces of lithostatic pressure, they act upon the bedded salt layers they can cause cracks and spalling on the rock that is exposed in the opening. And those rocks can come apart and they can fall into the opening, some of which are 25 feet tall. And as I said earlier, rock salt weighs 135 pounds per cubic foot. So that obviously becomes a hazard to the workers who are in these drifts or tunnels doing this operation. And so the force is equal to about 1 pound per square inch for every foot of earth that you have above that opening. And since we're at 2,150 feet underground, the forces that are felt on all the openings in the whip site are equal to 2,150 pounds per square inch. So that is quite a bit of force. If we don't mitigate that force that's trying to push the roof and the walls inward, then it could slough off. Some of that rock could break apart, it could slough off, and it could come down and it could strike or even bury miners who are working in our underground. So that could lead to, accidents or serious injuries or even fatalities. In the mining industry, rock falls are a serious occurrence that does lead to fatalities in many cases, and so it is the number one safety concern at the WIP facility and really in any mine. There's also the problem that the floor, which is also experiencing those forces from lithostatic pressure, it could buckle and it could heave upward. That makes the mine unsafe to travel in for vehicular traffic and for people who are traveling on foot. So all of those different things that could happen have to be controlled. That's what we call ground control. It's a program that we employ to make sure that we can maintain those openings safe to work in while we access these rooms where we're conducting this nuclear activity. The picture that you see in this particular slide is a diesel-powered roof bolter, and I will talk to you just briefly here about what a bolt is and how it is used in our ground control program and how it keeps us safe while we're in our underground. So this graphical representation that you see here is what happens to a mine opening when you mine it out inside of an underground facility. So there's some things to pay attention to here that are important. Of course, you see the opening. Actually, our openings are mined just like you see in this particular graphic. They're rectangular. So there are, straight walls and a straight floor and a flat roof to each one of the openings. Now, you can see that if you think about the opening being supported by a very simple pillar and beam system, the pillars are trying to expand into the opening. You see those forces there with the yellow arrows that are outlined in red. You can see that lithostatic pressure is continuously being applied to this opening, and both at the sides and the bottom and from the top. And you can see that above that opening, we have what we call the destabilized rock zone, and above that, a stable rock zone. Now, as I had said earlier, the Salado Formation is the remains of an ancient ocean that evaporated some 250 million years ago. And in the process of doing that, it was a gradual phenomenon. So it laid down layers of salt, and then in cases it would also lay down small layers of either clay or dirt, and they actually become seams in the future as more salt is evaporated on top of those. And so at depth where we conduct the WIP operation, about 8 feet above all of the mine openings is a clay seam. We call that the clay G layer. And that is above the destabilized rock zone. Above that is what we call the stable rock zone, which is, since it's far enough away from the opening, it is less likely to experience fractures and deformation that we see in the destabilized rock zone. So this just gives you an idea of the forces that are at work on every one of the mine openings that are inside of our facility. Now, I'll talk to you a little bit about a phenomenon that we call low angle fracture. So in this graphic here, you can see that that there are forces that when they are manifested on the opening, they're going to cause a phenomenon that's called low angle fracture. Now, when I tour people in our mine, I ask them, if you were to, take a guess about where the forces inside of this opening are manifested the most of them will say in the middle of the roof. And actually, it's where the horizontal and the vertical of the roof and the walls meet. That's where the forces tend to manifest themselves the most. And what will happen is you'll start to see microfractures that start to propagate from those corners, and then they will start moving upwards, or if they're coming from the bottom, they'll move downwards, and they will continue to move like that and coalesce into big, gigantic fractures. So eventually they're one fracture, and they'll propagate until something stops them. Usually, in our mind, it's the clay seam layer that's above the opening in that destabilized rock zone. Or they could actually run into each other and stop each other. But as you can see from the graphic, the result of that is that now there is a portion of that destabilized rock zone matrix which has been freed from the matrix, and it can fall into the underground. And this can be literally tons, even thousands of tons of material. So in order to prevent this freed rock falling into the opening, we have to mitigate this, to prevent it from doing that very thing. So low angle fracture is something that is of significant importance to us at the WIP facility. We have to understand it, we have to study it, we have to monitor it, and then we have to mitigate it. And the way that we mitigate it is that we will use bolts in order to pin that freed rock area up to that stable rock zone. So I will show you that here in our next slides. First of all, I want to show you some of the components that we use for what we call our ground control program. First of all, there are rock bolts, and it's not a great picture, but on the left picture that you see in this slide, in the middle of that, on the ground there, you can see a bolt. Now, they can be very long. They're 3/4-inch steel rebar bolts. They're threaded on one end, and they can be anywhere from 4 to 24 feet long, depending on how far you have to push a bolt up into the destabilized rock zone to get it into the stable rock zone. We also use chain link mesh. Now, it's not the standard chain link that you're going to see in your local neighborhood that's, dividing someone's yard from the street. This is actually very heavy-duty stuff that can hold up to 3,500 pounds per square foot. And sometimes we will even use things called crib sets. And crib sets are probably what you have traditionally seen in movies about mines. It's timbers that are stacked up from the floor of the opening all the way up to the ceiling of the opening, and it's just there to hold up the ceiling, if you will. It also has the added advantage of preventing roof falls that begin in the ceiling and keeping them from propagating past where you put the crib set. So those are just some of the components that we use for ground control. Now, the main component that we use, however, is a rock bolt. And this is sort of here's how a rock bolt works. Okay, so in the picture that you see here, you can see in that tear that you have past that chain link mesh, you can actually see the destabilized rock zone. This is an area that actually fell, and you can see the layers of salt that make up that destabilized rock zone. We call them laminates. And in the middle of that buckled laminate, that roof that you see there, you can actually see an old bolt that had at one time held that laminate together. So that's what rock bolts will do. We will actually pin the laminations in the destabilized rock zone together by adding that bolt to that. Usually we use shorter bolts for that. We call them mechanical bolts, and that's going to make that destabilized rock layer stay together and be more coherent. However, sometimes we have to anchor the entire piece of halite that has been freed by the low-angle fracture phenomenon, and we use longer bolts in that case. And those longer bolts will go all the way through the destabilized rock zone into the stable rock zone, and it's kind of like nailing drywall to a stud, if you will. Now, like I said earlier, at the end of those bolts, they're threaded. So we take a metal plate that has a hole in the center, and we put the bolt through that metal plate, and then we take a nut and we'll torque up that nut to that plate and get it up against the the ceiling, and that's what's going to pin that bolt onto the ceiling. So I actually have a graphical representation, I think, that shows that a little bit better. So you see here in this graphical representation, um, you have the destabilized rock zone. You have the stable rock zone above that. What we do is we'll drill holes through the destabilized rock zone into the stable rock zone, and they're about 20 feet deep. We'll push a resin packet up into that hole, and it has two components, and so it's not set yet. So they're just little packets that we'll push up into there. Then we take the bolt, and the bolting machine will push the bolt up into that same hole, and it will pierce that resin packet. Then we spin it with the resin, with the bolting machine. That will mix the two resins, and they set in about 30 seconds. Now, basically, it becomes part of the stable rock zone matrix, and it's very strong. It will hold that bolt in that resin packet and an additional 65,000 pounds, as a matter of fact. And as I said earlier, now after we have the bolt into the resin and the resin packet is set, then we'll take the plate, which has a hole in it, we'll basically put it around the bolt, and then the nut will push the plate up onto the ceiling. And then now what we have done is we have captured the weight of that area of rock that has been freed, and it's being held by the resin packet and the bolt in the stable rock zone. So you see on the right-hand side of this graphic, there's a picture, and it shows you one of the completed bolt assemblies. And so you can see the plate. You can see that the plate has been threaded up against the rock surface by the nut, and you can see the end of the bolt sticking out from the hole in the plate, and the portion that had gone through that was threaded through by the nut. Now we also put a lanyard on that nut so that we can capture any bolts that break. Now we have a bunch of these bolts in our underground. This is the main rock support system that we use to prevent rocks from the rock from falling on us. The long bolts again go through the destabilized rock zone, and they have the strength to hold up 65,000 pounds of weight. We only take credit for 45,000 pounds to give ourselves a little margin. Now, the question I get often about this is, how do you know how many bolts to put in to the rock in order to stabilize the freed rock that from the low angle fracture phenomenon? Well, number one, we have a lot of experience. We've been doing this for 30 years now. And as a matter of fact, in the picture that you see there, there's obviously a pattern of bolts that we put in there. And over the years, we've learned that if we do this, if we put 7 bolts in a room where we place waste all the way from one wall to the next, and then 5 feet later we put another row of those bolts, that will be enough bolts to hold up any rock that destabilizes and wants to fall. So this is something that we've learned over the years. But if you happen to be able to, let's say that you have a low angle fracture phenomenon occurring, you can drill up into that destabilized rock, and then you can put a scratching tool that will go up and find where the rock is separating from the matrix. Now you know how thick the rock is, and if you know the area that is being impacted that's starting to come down, which you can do with sounding tools or sonic tools, then you'll be able to tell just how big an area of free rock that you have. And since you know that halite weighs 135 pounds per cubic foot, now you know how much steel you need in order to hold up that piece of freed rock that's there. We will install enough bolts that we have a safety factor. As a matter of fact, we put enough bolts in that it can carry 1.5 times the weight of whatever we've calculated that would be able to fall from the destabilized rock zone. This is an intense operation for us. We have over 90,000 of these bolts that are in our roof and our walls in our underground that are holding up the ceiling or the back. As a matter of fact, if you ever visit WIP and you go into our underground, it is the only place in the DOE complex where you can work under a suspended load, which is always true in whip. Now, the bolts will fail, they will break from the forces that they are feeling in the underground. There's two ways for our bolts to break. They can either be sheared by shear stress, and that's caused by the laminate layers that you saw in that picture earlier, moving against each other, sliding against each other. They'll actually slide enough that they will actually snap the bolt somewhere along its length, right in half, or along the length somewhere. And so that's why we have the lanyard, to capture the lower portion of the bolt that was broken by that shear. The rock can also move downward. It can start to sag, and as it sags, it will actually move around the bolt and the plate, and it appears as if it's sucking the bolt and the plate up into the rock matrix. And as it does that, it's stretching the bolt, and at some point you will reach breaking strength for those bolts, and they will snap from tension. So either shear stress or tension stress will break our bolts. On average, in our underground, we lose 2 to 5 bolts to those stresses every day, and about 20 to 30 of those bolts every week. And so they must be replaced, because if you have lost a bolt that has been holding up some portion of the weight of this suspended rock, and you break that bolt, the bolts around it are going to have to take up those forces, and so they will be weakened, or they will fail at a quicker pace than they did before. So every bolt that breaks, we have to replace it. That's why the bolting operation is so important and so intense in our underground. If any of the areas in our underground, we measure the safety factor by the number of bolts that we have that are intact, that are not broken, knowing the weight of the rock that we know that is free, and we maintain a 1.5 safety factor. If we ever go below that in any area of the mine, we will add bolts to make sure that we maintain it at that safety factor, so that we have some margin. So there is also a phenomenon called roof sag or belly that we sometimes see in our underground. These pictures that you see here in this particular slide don't really do it justice. This is sometimes difficult to explain, but hopefully you can see what I'm going to do here on the screen. So think of, if you will, think of the openings in the mine as a very simple post and beam system. So the walls are the posts, and the roof is the beam. And so if you have lithostatic pressure that is acting on the walls at all times, they're going to try and push the walls inward into that opening. And as you can see, the walls will actually start to lean. If you come into my underground and come to some of the older drifts, it is absolutely, you can see absolutely that the walls appear to be leaning inward. And as they do that, they're compressing the beam that they are holding up. And so we see a phenomenon like this. This is a card that I'm holding here. It will start to sag from the beam being compressed by the top of the posts that are holding it up. That causes the belly or the sag in the roof, and you can see that in the pictures here that I have before you. So the problem with that is that, number one, it's deforming the rock, and it will in some cases start to rubbleize. It will also impact the bolts. It will kind of defeat the purpose of the bolts if it starts to rubbleize around the bolts. And so we have other strategies that we use to try, and when we really start to see deformed rock layers, to try and hold those up. We actually put slings in some cases and create a basket with wire slings that will hold that belly in place. There are some places in our underground where this belly has deformed by as much as 10 feet. And so it can be quite disconcerting to see, but what I'll tell you is that we measure the convergence rates sometimes, in many cases, daily, but definitely weekly, depending on the acceleration that we see in the convergence rates. We actually do it with measuring sticks or with measuring tape that are thousandths of a degree of an inch. And so we can see how many inches per year the roof and the walls are sagging towards each other. And If we ever see that accelerate, then we can go in and we can put in more bolts, or we can put in more slings, or we can decide, you know what, we just don't need to be there and we can get out of that area. So I'll tell you that these areas that you see here, which are sagging, we have enough bolts in place to hold that rock in place, and we are in control of the convergence rates. And I would take you all down there with me. I would take my mother down there to these areas. But when they become dangerous, that's when we would prohibit them and we would get people out of those areas. So we have an entire geotechnical group, engineers, who this is what their job is. They do this every day in every area of the mine, and all 8 miles worth of drifts that we have in our underground. They're keeping very close eyes, and they monitor the movement in all those areas and inform our underground operators what they should be doing to keep them safe. So I did mention earlier the chain link mesh. That is for loose, unconsolidated rock that gets crumbled or rubbleized as the rock is moving and it's trying to fall down. They tend to rubbleize along the edges where the horizontal meets the vertical, and this very thick chain link just captures it. Once in a while, we have to open it up and empty out an area of chain link that would be collecting lots of loose and unconsolidated rock. Almost done here. This is a picture of one of the bolting machines that we have. Interesting units. You can see that there's a boom that comes off of this machine. These are diesel powered, although we have some hybrid bolters that can run off of electricity as well. There's a cab, and an operator, a miner, will be in this cab, and the boom can extend outward and upward, and this is where he will apply the drill steel and drill the holes into the back, and then push the bolts up through the holes that he's created, and the resin packets and all of that. These things are not nimble, okay? We have 6 of these units, and they are all employed pretty much at all times, and so we have to tram them to any area of the mine where we need to put bolts in, where we're having bolt failure, and then we have to put the outriggers out. We have to get set up. There's a whole crew that does this, 6 crews, as a matter of fact, that are working on each of the individual miners. And then they have a considerable amount of maintenance that we have to maintain to keep them operational. So sometimes we don't have all 6 miners employed because either they're in their PM cycle or we're doing some sort of repair to them. These units have hydraulics that apply the force that we can drill through the rock, and there are in the neighborhood of 400 to 600 hoses on each one of these machines that have to deliver the hydraulic fluid in the manner in which we need to deliver them. So if you have that many hoses, you're going to develop leaks over time, and we have to replace those hoses when that occurs. And so this is a very intense, very high activity thing that we do, because we have to keep bolters running at all times to maintain the mine in a safe condition. This is my last slide. This is a picture of what happens when ground control is not successful. You can see here, this is actually in the mine by panel 4 in our underground, which is one of the most southerly panels, which a panel is an area where we drill out rooms in order to put the waste in. And there was a rock fall here. I'm going to say this was in the neighborhood of 2,500 tons of rock. And it fell probably in about 10 seconds or so. As you can see, the bolting pattern was overcome. Now, our geotechnical engineers saw this coming. They were measuring the convergence rates, and they saw that they were accelerating, and it was obvious that our bolting activity was no longer going to be successful. So we got everybody out of there. We barriered off the area. We prohibited it, and then we allowed Mother Nature to do what she was going to do. And you can see here that it's quite a bit of rock. I have the silhouette of what a average-sized person standing there would look like. So you can see that this is a true existential threat to any mining community or mine that is operating in the United States. And so in the time that I have had the privilege to work here at the WIP site, we have experienced 6 rock falls. All of them we saw coming before they were going to happen. As a matter of fact, the closest that we predicted that a rock fall would occur, and then it actually did occur, was 21 days. Usually when we predict rock falls, they happen anywhere in the neighborhood of a month to several months So we make sure that we have plenty of margin if there's an area of the underground that we cannot control. So that is it. Those are all of my slides. I would welcome any questions that anybody would have about ground control.
Well, thank you, Mr. Garza, for that presentation. So now let's open the floor for questions. Do we have any questions from the audience?
I have a question.
I have a question too. Sorry.
Oh, you can go first.
Thank you for the presentation, Mr. Garza. My name's Autumn Taylor. I work in Dr. Cossen's group here at Vanderbilt. I was just curious, in any of these rockfall scenarios, does the ground control ever try and go in and reopen those areas after they've collapsed, or are they done for good?
Well, generally, the ground falls have occurred in areas where we've already completed the operation. And so, again, as I had said earlier, we have, through experience, determined that if we put in a certain pattern, that's going to maintain the area safe for the operation for the operational period. And then we leave there and we're no longer doing operations there actively, but the areas are still maintained open so that we can go and monitor things as they're occurring. And normally, those rock falls have occurred in areas where we really don't need to go back to. So the answer in that case would be normally no, but we have had in our panel 7 of our underground, which was the previous panel that we were operating in before we started panel 8. In that case, it was an older facility or older dig or excavation. We had some rock falls in some of the rooms that we were going to utilize, and we did go in and we mined out that fallen rock, and then we restabilized the back, and we conducted the operation in that area. I think it would be situational, but actually kind of rare that we would want to ever do something like that.
Thank you.
You're welcome. Thank you for the question.
Jody, you had a question?
Well, my question was very similar to what Autumn was going to ask. Once you have rockfall, does it continue? Do you have other situations where it continues to crumble and to take up, collapse?
Well, that is an excellent question. Okay, so again, if you think about the geology or the makeup of the matrix of the rock, in the destabilized rock zone, it is laminates, and so they run, north, south, east, west. They run perpendicular to the walls. Okay, and so if they begin to fall, it's like a slab that's separating. If the slab on the bottom separates, then it will begin to fall, and it could propagate, or we call it zippering. It could zipper continually along that seam until it reached something that would stop it or disturb it, if you will. So if we have areas of our underground in the drifts where we've determined that, we're no longer going to be successful to hold back the rock, to keep it pinned up, if you will, to the stable zone, then we will abandon that area. We'll put in barriers to physically prevent people from going in. And then outside of that barrier, we will put up what we call a bolt brace. It's basically intense bolting that goes up into the stable rock zone and forms a barrier. Or we'll put up those crib sets that I showed you earlier, and they will add stability to that slab, and they will actually stop a fall that is propagating out towards those areas where we normally occupy. And we have a lot of experience with this, and we're very successful with this. We've never had a rock fall that has continued out into an area that we normally occupy. And I'm going to knock on wood that we can continue to do that. We have some of the best geotechnical engineers in the world who have kept this place operating for 30 years now.
Thank you. That definitely answered my question.
Yeah, okay, great. Excellent. Yeah,
Hello.
next question.
Hello, Ian. Garza, thank you very much for the presentation. I have one question regarding to this fall. So you said it's important to kind of avoid any damage through this fall. You need to monitor the roof to predict the fall, right? So you can avoid any damage. But my question is, this is a pretty local issue according to your whole facility, right? It only happens at one place, but how did you design the distribution of your sensor, right? So, and how much sensor do you need to catch this issue before it happens? So, yeah.
So, well, I think there's a couple of questions in that. And those are both great questions and thoughts. Okay, so number one, do we do the design of the openings to try and minimize rock falls?
Mm-hmm.
The answer to that is yes and no. Okay, so there are designs that are better than the current design that we have in our underground that would make it less favorable for separations in the rock. Just in general, people think that, well, if I need to distribute forces so that they are equally distributed into some sort of, geological opening, a round shape is probably the best one to go with. And so we've thought about that quite often, but the problem is that much of the mining equipment is designed to access a flat opening. And
Mm-hmm.
so hence we would, if we did that, and there are some facilities that actually do that, we would have to probably have mining equipment that was made specifically for the shape or the geometry that we formed in our underground. So we have gone with the traditional method in this case. Now, to predict when the rock is going to fall, we actually do have quite a bit of equipment that we use to do that. So the first thing we do is, of course, is visual. So, all the miners who are in the underground are looking at the condition of the ground before they go to work, while they're working, and as they leave, they look at that condition. They report anything that they see as abnormal, and they're all trained to some degree in how the geology works in our underground. They report that to the geotechnical group, who then will go and investigate. The geotechnical group will go into our underground, and every day, before we start operations, and they do a visual inspection to see if there's anything from a visual perspective that has changed so that they can then decide whether they need to apply some sort of mitigation or decide if we need to prohibit people from those areas, that kind of thing. Now we have machines that actually monitor the strain in the rock. We call them extensometers. And so we will drill holes up into the roof, up to 20 feet deep, and then basically we're putting in strain gauges. And those strain gauges will measure tension in the rock layers, and as we see that tension go up, that tells us that we might have the forces that are accelerating in that area, and so then we need to go and pay more attention to there, or maybe put in more bolts, if you will. We can drill holes into the rock, and we can actually look into that hole, and we can see if there are separations that are starting to occur, and we can measure with measuring sticks to see them and watch them grow. Another thing that can tell us if we have something that's about to happen. And finally, we can measure the convergence rate. And we map that over time in literally hundreds of areas of the mine. And as we see the convergence rate accelerating, most of the areas in our mine are in a few inches per year of convergence rate. So the walls and the floor and the roof are all coming in 1 to 2 inches per year, every year. If it starts to accelerate, we can put in more bolts or different ground control measures to abate that. Now, we can never stop it, but we can slow it down. And so there's such a science to this. That's such a great question. There's new technology that's coming out, and our geotechnical group is getting to the point now that we have some younger guys and ladies who are getting into the group who are ready to embrace new technology like LiDAR, which can show you the movement of the opening down to very, very small measurements so that you can see where those forces are being manifested. And we're also looking at an integrated system that can measure the forces that we're seeing, the strain in the back and the walls and the floor, and then look at it holistically to see if we can predict. The last thing I'll tell you about, it's you, right? The last thing I'll tell you about is that there's actually a method of mining so that you make the pillars, the posts that I was talking about earlier, if you can make them actually a little thinner in the area that you have disturbed overall, that actually spreads the forces out to the abutment pillars on the edges of the mine, and it can actually cause the roof to become much more stable and not so susceptible to this low angle fracture phenomenon. So yes, tons of ways to do it. tons of technology with which to do it, and like I said, it is both science and very much an art for the people that do this. So excellent question. Thank you for that.
Yeah, thank you. Yeah. I'm glad the geotechnical engineer always helpful because I'm supposed to be one of them.
Any other questions?
Do we have any other questions for Mr. Garza? I think just when you were presenting, I think in one of the slides you mentioned that you lose around like 20 to 30 bowls per week or something. So I'm just like curious, how do you like, is it by visual inspection? Like what sort of maintenance goes into it to just keep a tab of all, like there were so many bowls in there. Is it just a visual inspection on a, I don't know, daily basis or something?
Yes, it's visual. When a bolt breaks, it is obvious, okay? Because if it breaks by tension, it might actually try to shoot out of that hole that we created, but the lanyard will catch it. If it breaks by shear stress, now basically if it isn't captured in the rock matrix, it's free to fall out of the hole, and so it will try to fall out of the hole, and then the lanyard will. Okay. So in most cases, it's quite obvious. As the plates are being impacted by rock that's moving or expanding around them, the plates will begin to deform, and you can see that deformation in the plate. See the plate begin to get concave, and so you know that it's happening, that there is tension in this case. And so the geotechnical group has a map of the mine and all the bolts, believe it or not, all 90,000 of them, and so they watch areas at a time, and our experience is that the forces begin to manifest themselves in a certain area, and so we see bolt breakages in those areas. We'll go in, we'll remove the old bolts, we'll put in new ones, and we'll label them, and then they get tracked to see how long it is before they begin to deform, and it gives them a good idea about where they need to have their attention. Every 2 weeks we have a ground control meeting, and we talk about how many bolts we've replaced and where we believe our top 5 areas are that we need to be bolting, and then we use that to inform the mining crews that go in and do that operation every day.
Okay, thank you.
The last thing I would leave you all with is that, there is a nuclear threat, not nuclear, there's a radiological threat in our underground because we're handling nuclear waste. And it is well respected, and our controls are well developed, but it is not really the existential threat that we have here. In my 37 years, or actually it's 37, I forgot to add it up correctly, in the nuclear industry, what I tell people is that I have yet in my time to see anyone get contaminated to death. Okay, I mean, again, the plutonium, the uranium, and the isotopes are a threat. But in the mining industry, fatalities, unfortunately, are something that happens, and not rarely. And so that is the real threat here at this facility. We must keep the ground safe. And without safe ground, there is no WIP. There is no nuclear activity. So that's why it's so important to me and to all the miners here. I really thank you all for your time and attention, and I would love to see any of you come here and visit us at some time and see our underground, actually come down here and see what we do. So thank you very much for this opportunity.
Okay. Thank you, Dr. Garza, for talking to all of us. And with that, we'll wrap it up. And I wish all of you have a great rest of your day and a good weekend coming up soon.
Bye-bye now.
Bye. Thank you, everyone. Bye.